My name's Trevor, and I'm going to be talking a little bit about a climate services tool that we've been working on for about 5 years now. So I'll begin by talking about why we built the library, how we built it to be useful for multiple types of activities, go over a bit of the internals, as well as a live demonstration, and I'll end with the credits. So before anything, what is Oranos? So Oranos is a consortium of around 60 researchers, educators, and project managers based out of Montreal, Quebec, Canada. And our goal is to provide approachable and specific climate information for various stakeholders in the province of Quebec and internationally. We're a climate service provider, so we concern ourselves with transforming research and simulation data into simple and useful plots or tables, things that are easy for people to digest. We also run our own regional climate model experiments, and so we're very familiar with working with very large data. So myself is Trevor James Smith. I'm I'm in the climate platforms data and operations team alongside my my partner for this presentation. Unfortunately, he couldn't be here, Pascal Bourgault. So before anything, it's always good to know why we're doing the things that we are doing. And yeah, climate change is occurring on Earth. Life is on Earth, and it's going to affect life. So a lot of people are concerned. The United Nations has the Sustainable Development Goals. So number 13 is taking climate action. I put the climate clock in New York as well. So what can we do about it? Well, we have physics, we have programming, we can generate climate models, which leads to making experiments. And hopefully from these experiments, we can get actionable information. But there's a bit of a problem because everybody's making climate models, everybody's running experiments. There's more and more data, more and more problems that we have to deal with. In the bottom here, this is just kind of an example of all these different model simulations of Earth's climate. And well, none of them are correct. There's lots of variability. There's lots of internal changes, internal differences between all the different models. And so we have to figure out how to make extract the useful information out of all this. At the same time, we're also having to deal with model data, which is growing and growing in size with every year. So this is just a graph projecting change from 2010 into 2030, and the volume of data is just constantly growing as models become more numerous in their number. Experiments are more numerous, and simulations are run for many different reasons. So what are we doing about it? Well, one way that we can tackle this is by creating climate data platforms. So one thing we can do is generating these kind of like portraits or platforms that give us a way of searching through the data and getting useful things out of it. So Canada has ClimateData.ca. Quebec, we offer one called, whoops, I pressed the wrong thing. Yeah, so we have one that's called Pavix. And in Europe, we have Copernicus, and there's plenty others like the Microsoft Planetary Computer. But is that helping? Well, it does, because we have more relevant, customized, specific information. We are using less bandwidth. We're not having to download enormous chunks of data in order to get the things that we need. Makes it a lot more available. And then ultimately, we're spending more time doing research and less time managing data. So this is one example here of ClimateData.ca. What we can do through this platform is we can choose a data set. We can select a particular location. This is Montreal. We can choose variables to work on. We can choose a time frame. And because we're dealing with large groups of models, maybe we want to have ensemble statistics like the 10th, the 90th, the 50th percentile according to some emission scenario. So here we have, this is degree days below a threshold. Maybe I'm curious about that because I'm concerned about hockey rinks being available in the future. Maybe it's going to be too warm for us to have outdoor hockey rinks. I hope not. Behind all that is Xclim. So Xclim is an operational library that we've been building for a long time. And we ideally want to, well, the reason why we did it was to have control over our algorithms, and ensure that standards are good, and have transparency of the code. So developing software to better serve our needs, the idea behind that was, at the time, we were a bunch of researchers. We had our own ways of doing things, and ensuring that results are replicable even within our team was very challenging. So we wanted to build a tool that we could all use internally. And then additionally, we wanted to have this tool be able to be an engine that could power things such as ClimateData.ca. So yeah, our design goals was it had to deal with big data. We wanted to have asynchronous I/O and fast analysis, and we were able to get that with xarray, dask, and numba. We wanted common standard climate indexes for our team. We wanted climate metadata that adheres to the standards that you would expect of climate and forecasting. And then also we wanted to have it open source. We wanted to be able to show our work and be able to benefit from contributions. So yeah, in many cases, climate indexes they can be calculated almost as one-liners. It might be like a mean over time based on temperature. That would give you your mean temperature. But we wanted it to do a little bit more than that, because there's a lot of kind of intricacies to working with climate data. There's the concerns about units management. So if we're working with temperature data that's in Kelvin versus Fahrenheit, that's something that we need to think about. Ensuring that the metadata is correct is really important for us. And then dealing with things like ensemble statistics for large ensembles of models. Every model has bias, so we need to figure out how to deal with that. And then we wanted to make sure that there was data quality assurance checks in addition to that. So in our implementation, we were aiming for something that was operational, foolproof, and able to be built upon. And yeah, just to mention, a climate indicator is any function that summarizes weather information into climate scale information. So this could be simple to statistics over a certain time frame, so mean temperature, number of days of precipitation, etc. Yeah, so for the average user, maybe they might just be concerned with indicators, but we've actually built this tool into being something that is much larger than that. So we have our ensemble module. We have a statistical and bias adjustment, statistical downscaling and bias adjustment module. We have utilities for dealing with different calendars, missing units, things like that. As of December, we're at version 0.47. So that gives us around 187 official climate indicators, and around 90 of these deal with precipitation and temperature alone. So as I mentioned, yeah, we were building this with dask and numpy and numba, and xarray. And so one thing that we were able to do, because we're sticking so close to that stack, is our data structure is very easy to be used with the Pangeo data structure as well. So we can do things like we can pass our data objects to pretty much anything that's built on pandas or xarray. And vice versa. And then for our statistical algorithms, we're sticking everything is in the open source realm. So we're still using dask, we're still using pandas, numpy, but we've also built a few things of our own. And we've sped that all up using things like numba. In order to ensure that our metadata and all the units and conventions are good, we're basing ourselves on CFXarray, which is it's an xarray-based or climate and forecasting conventions tool. And so that ensures that we're able to have the proper dimensions that you would expect from climate and forecasting data, with Pint used for unit conversion. Yeah, and we're planning on moving this to Pint xarray very soon. We have our own we have a whole module for Pint that we're trying to move that up. And we've already in the past, we've moved quite a lot of things upstream as well. So we've made contributions to CF time. We've made contributions for calendar conversion and xarray, Pint as well. We've even moved a few things into NumPy, and we also maintain and regularly do pushes to things like XESMF, intake ESMF, CFX array, things like that. So internally, we divide. So the indicator module is probably the largest module, and is what most people will use. And we've divided this into two kind of synonymous APIs. So one API is for, we call it the indicator API, and then the other one is called the indices API. So if you want to, if you don't care about all the metadata checks and all that, what you can do is you can say, I just want to run. I want to run a computation. It'll do maybe an input unit check to make sure. Well, if you're passing temperature data to something that works only on precipitation, it's going to say you can't do that, and then it will do the computation, and it will give you something exactly back, which will be an xarray object with a NumPy or a dask array. Or if you want kind of like everything else. So this would include checks to make sure that the metadata is good, that your cell methods are good, your frequency checks, so making sure that the data is in the proper time frequency. That's all performed before you even hit computation. And then after that, we'll do things like ensuring that the units are good. And we can do things, additional things like ensuring that if there's any slices that have too much missing data, then we're going to drop them because we don't consider them valid. And finally, we can do things like adding very specific metadata. So that kind of makes it foolproof and more of an operational tool than anything else. And so what we want to do on top of this, so I mean, if we can ensure that we're always getting the same things out, we can also extend upon this. So there's two ways that we can extend Xclim. So one way is to literally just add new indicators directly into Xclim, and you can add a pull request if you want. But we also built a way of making, we call them virtual submodules. So this would be if we wanted to create a library, like an extra library based on the like a generic set of climate indices or indexes. We could write this all out using this kind of like YAML configuration and say, we want to use the count occurrences indice using minimum temperature data. We're like doing a sum. We want to make sure that our metadata looks good at the end. And these are the parameters that we're passing through it. And so you can essentially build your own module if you so desire, and that will give you the data that you expect. Yeah, so the last segment here is the bias adjustment module. So for those who are unfamiliar with climate model outputs, they're very similar to any other model output where you need to correct what's coming out. What we have coming from a model data, it's often too hot or too cold, and you need to ensure that the distribution of values is compares well with today. I'm not the statistician on the team, but if ever you have a question, feel free to ask it in our GitHub. So I wanted to make sure that there's enough time for the live demonstration. So I'll see if this works. Okay. Here we go. Are you able to see it? Okay, I'll assume that you do. All right, so hello? Oh my God. All right, I'm going to assume that this is good. Yeah, so for this, I'm going to give a really small analysis or a really small kind of a playthrough of this. So this is just showing what we can do with Xclim right off the bat. So I'm going to start with the first demo, which is the climate indicator calculation. So this is going to just show that calculations are that we can kind of like work with unit management and things like that, and missing data. I'll just start here. So this first demo is on the indicator calculation and unit management. So we want to calculate monthly growing days above 5 degrees Celsius. We want to ensure that there's identical results regardless of our input. So if we're playing with Kelvin or Fahrenheit or Celsius, and we want to ensure that we want to ensure that that everything is entirely consistent. So in this example here, we're importing Xclim. We're using the growing degree days indicator. So we have our temperature in Celsius with a threshold in Celsius. We have a temperature in Fahrenheit with a threshold in Celsius, and then our Fahrenheit temperature and a Kelvin example here. So if we run this, you can see right off the bat that no matter what you give it, it's always going to be consistent. So this is very important when we're working with data that's coming in different units, or maybe if we want to ensure that we're getting a specific unit out. This is very useful that we don't have to deal with this ourselves. For missing data, there's a whole bunch of ways that we can kind of handle the missing data problem. So missing data can happen very often with observed data sets, so things coming from stations. It's a major concern, and if we want to be able to be using it properly for some statistical reason, then we need to ensure that we're dropping the slices that are no good. So a couple ways that we can do that is by using the World Meteorological Organization standards. We can have a percentage of missing data that's allowed per slice. We can also just have an arbitrary count of missing values that's allowed, or and there's a few other ways that we can do it. So here we're setting tolerances here for 25% and 5%. And we're concerned about, we're using temperature or min temperature in order to calculate our ice days. So ice days are being temperatures or days where the maximum temperature is below 0 degrees Celsius. So if we run this, it's quite fast. We can see here that when we have a threshold of 25% missing data, we have 101 valid years for the station that we're looking at here. And then if we're a little bit more stringent, then it's going to start removing it's going to start removing years where there's more missing data. So this is very useful for, if you want to do an analysis in an area that has very sparse readings, we kind of leave it up to you to be able to play around with that. Given that we're operating in Quebec, one thing that we want to do is we want to ensure that our metadata is in French. So we built our own internationalization like metadata standards. So with this, we can set our metadata locale to FR for French. And we can see that in our attributes here, we have our standard name. So this is a controlled vocabulary coming from the climate and forecasting conventions. Our long name, which is kind of like an explanation. And you'll notice that the long name will have the thresholds and relevant information directly put into there. So we passed for this. This is mean temperature with days with mean temperature above 5 degrees Celsius. And so here we go. And then we have it in French as well, and it's syntactically correct. So that's fantastic. So we then have our ensembles of climate simulations. So this is very important when we're doing analyses based on multiple models. And so if we want to be able to kind of get some ensemble statistics, what we can do is we can start by, loading our data. So this is a data set that we have available on our Pavix platform. And then we're going to kind of like compare and see how we can put that together. So we start by creating an ensemble. Well, actually, sorry, I'll just say really quickly here that one thing that we need to manage here is that there are multiple calendars for these data. So some models use a 360-day year, some of them use a no leap year, and some use the standard calendar. And that's something that is a challenge to deal with. And we've actually, with our ensemble module, we actually are able to put this all together and ensure that any data, days, we can synchronize the days properly using a variety of different options. So That's all done under the hood. If you don't want to go into it, you don't have to. So that's one of the beauties of this. So running this, we're able to see, okay, well, we have all of this climate model data, and it's this beautiful rainbow spaghetti, which doesn't really tell us much. But if we want, what we can do is we can take the start running percentiles. We can do a percentile analysis to do the 10th, the 50th, the 90th, and then running this, we get the spread of possible values. So this is done, and I mean this is being done on a very large data set very quickly, and it's all with the help of dask. So I'll just show really quickly here that our entire module or our library is fully consistent with dask. So if you load things with xarray using chunks, you're going to get dask arrays, which are only calculated when you ask for it. So that's kind of cool. So yeah, so I mean, even if you say you want to do a particular analysis, it can be it's not going to give you any value until you ask for one. So I'm not going to run this because it takes a little bit of time, but essentially you'll only run the analysis when you need it. Yeah, I see that I'm running a bit low on time, so I think I'm going to switch back. Here we go. Yeah, and I'll just say that here that so who's using Xclim? Lots of people. There's Xclim, there's ClimateData.ca, there's a whole bunch. We've even have a few examples of Xclim being used in the Microsoft Planetary Computer. We use it as well internally in our PAVX platform, as you just saw. And we're also we're producing our own data sets using this this library as well. We also use it in XN, which is another offering from Oranos that does workflows. And we're at 270 stars on GitHub. So what's next? The last thing that we were working on, well, the things that we want to work on next is that we want to have algorithm improvements to make them a little bit more zippier. We want our documentation to be a little bit more clean, and then more of just building out more things, maybe more realms, more indicators, things like that. We're going to be migrating some functions upstream. And then we've been in version 0 for a very long time. So we're thinking of maybe going to version 1. I asked the same thing to ChatGPT, and it gave me pretty much exactly what I expected. And it's exactly what we were planning. And that was a little bit terrifying, but it's good to know that we're on the right track. So who's behind it? I just want to thank the core development team, so Pascal, who couldn't be here, like all of these people, our contributors, and if you ever feel the need to look at what we have, please feel free to read our paper which published in JOS recently, or check out our GitHub. Thank you very much.
Fantastic. Thank you for the talk.
Yeah.
We've got 5 minutes left. If there are any questions anyone might have, feel free to put them in the chat.
Yeah, I see here. Yeah, so from Aid, Trevor, very interesting talk. Sorry, I missed this during the presentation. In what context are you using xarray data structure library in Xclim? In what context are you using xarray data? Well, I think, so Xclim is entirely based on xarray. So so long as you pass any type of xarray object, so we mostly work on data arrays, it will understand and it will give you exactly what you expect. We're working on some new features to kind of start passing directly data sets so that we can do things like managing the global attributes. But right now we have a very, very strong data array management. Like the entire library is built around that. So yeah, funny enough, one thing that ChatGPT mentioned was that we should try operating on pandas arrays, and that actually had got us thinking that maybe that's not a terrible idea. So we might be doing that in the future. Anyway, So yeah, how large of ensemble datasets have you been able to generate graphs for? What were the runtimes? So we, well, right now we're developing a set or two, I guess, yeah, two sets of climate data that are available. Well, they will be available soon publicly, but right now they're currently under review, and they are 10-kilometer. They're 10-kilometer regional data sets for, I think, at least 8 or 9 climate variables covering the entirety of North America. So crunching that, you do need some power behind that, but the fact that we can crunch that on like our workstations is really cool. Like Dask is super powerful for being able to do that. Previously we put out similar products in the past using the NetCDF4 library and lots of kind of like ways to cheat the fact that like we couldn't hold the data in memory. And running that would take months. And now we're creating much higher resolution data, and it's taking maybe, I don't know, a week to really put something out. So it's like night and day. It's quite impressive. And I mean, just that example before where I was looking at the ensemble analysis, like running that took about, I don't know, maybe it takes about a minute or so using 4 CPUs. And it's a very large data set. We're talking in the hundreds of terabyte scale. Or no, yeah, no, hundreds of I think it's hundreds of gigabytes that scale. Anyway, but it's quite performant. We've benchmarked it a little bit. Yeah, so yeah, please feel free to check out our website. Check out ornosync/Xclim. We generally get back to people within 24 hours, and if ever you have a question or you want to add something, we love it. It's fantastic. Yeah, so thank you so much for having me, and I hope everyone has a good rest of your conference.